What is Calculus 1 really about? We must first try to answer this question, in order to much more easily grasp the computational methods that are explored throughout the standard calculus sequence. Calling this course Calculus 1 or just Calculus is almost a lie by omission, because the name of the subject in full is infinitesimal calculus, or to really oversimplify things, calculations using infinitesimals. So we will open our discussion of calculus by first exploring what infinitesimals are, and hand in hand with this, where and how infinitesimals appear. We will then be ready to introduce ourselves to derivatives and integrals, which make up the computational bulk of calculus. As you will see in this video, derivatives and integrals are similar to each other, because they share the same conceptual underpinning. After this, we will briefly touch upon the scope of the standard Calculus 1 course. One thing to keep in mind as we discuss infinitesimals is that they are not so much complex as they are confusing at first. So in order to mitigate this confusion, we will not separate our discussions of what infinitesimals are from where and how infinitesimals appear. In fact, we will begin by exploring the natural habitat of infinitesimals to see how they emerge. Let's look at the function y equals to 2x, and let's observe a point as it moves along the curve of the function, getting closer and closer to the origin. As the point moves along the curve, let's track two interesting values. The first value is the y-coordinate divided by the x-coordinate. The second value is the y-coordinate minus the x-coordinate. So at point 100, 200, which lies on the curve, the ratio of the two coordinates is 200 over 100 equals to 2, and the difference between the y and the x-coordinate equals 200 minus 100, or 100. Now let's see what happens when this point reaches x equals to 50. The ratio 100 over 50 is still 2, but the difference 100 minus 50 is now 50. Skip ahead to 1, 2. And again, y over x, 2 over 1 equals to 2, and y minus x, 2 minus 1 equals to 1. So we can see a trend here. Y over x remains 2 no matter what point you are looking at on the curve. But y minus x, the difference between the coordinates, is decreasing as the point moves closer and closer to the origin. Now this raises a question. What does the triangle formed by the y and the x coordinates of the point and the curve of the function y equals to 2x begin to look like as the point approaches the origin? You could imagine that as the difference between the y and the x coordinates of the point approaches 0, the triangle becomes more and more similar to a triangle with legs of equal length. But this is strange, because we know that the slope of the curve y equals to 2x is equal to 2, y over x equals to 2 at any point. So how is it possible for a triangle with legs of equal length to have a slope that is not equal to 1? This does not make sense to us by definition of slope. In order to preserve a slope of 2, we need to make sure that the value of the y-coordinate is always equals to twice the value of the x-coordinate. This presents us with a new challenge. As the point approaches the origin, the value of the y-coordinate approaches the value of the x-coordinate because y minus x approaches 0. At the origin, y does indeed equal to both x and 2x because x equals to 0. But what happens to the triangle? How does the ratio of rise over run morph from 2 to 1? Let's try to identify where this transformation occurs. No matter where this point is, there is always a value smaller than its x-coordinate, for which the x and the y-coordinates of the point would not be equal to each other. So there is no smallest positive real number. As mathematicians, we are free to define our own value type, which we can then set the x to. Let's call this value type an infinitesimal, and let's define an infinitesimal as a positive value that is strictly less than any possible positive real number. Why is it valid for us to use these made-up values to analyze functions from a real number line to a real number line. This is because an infinitesimal is an intellectual aid, which helps us analyze what happens to the relationship between the x and the y coordinates as they become smaller and smaller. I will describe in a moment what I mean by this. In the calculus context, we call infinitesimals differentials and label them by d of the name of the variable, in our case dx. So we will replace our x's by dx's. And in fact, the 2dx is an infinitesimal length along the y-axis, so we will call it dy. This could also be written as dy over dx or dy dx, as it is read, equals to 2. What does this ratio of two non-numbers mean? Well, let's look at a general slope of the curve y equals to 2x for any y and x values. We know that for any x value along the x-axis, there is a unique y value that is mapped to by this function, and for every y value, there is a unique x value that is mapped to it, because the function is invertible. And this is true of any x and y values. So we see that while the length of the rise is twice that of the run, y equals to 2x, both the rise and the run have an equal number of points, which are mapped one-to-one to each other. Now we can see the full picture. As the point approaches the origin, the values of the y and the x coordinates become very, very small, and they approach each other in value, but their ratio remains the same. When the point finally reaches the origin, x equals to y equals to 0, so it is still fair to say that y equals to 2x, but it is also fair to say that y equals to x, and that y equals to 100x. By labeling the legs of this triangle dy and dx, we are telling ourselves that this triangle is compressing into a point. And by setting dy equals to 2dx, we are essentially crystallizing the relationship between the x-axis and the y-axis at that point. So dy over dx equals to 2 tells us that at the origin, which is the point under consideration, the x-axis is stretched 2 times by the linear function. Therefore, the slope of the curve of the function at the origin equals to 2. This identifies 2 as the most natural relationship between the x and the y-axis at that point in this function. This relationship is natural because this notation explicitly specifies that as the point hits the origin, the ratio of y over x is still thought of as 2 rather than jumping to some other random value. What does it mean when we say that the stretch at the origin equals to 2? Let's add some meaning to this setup. Suppose that y equals to 2x represents the position of a car in meters over time in seconds. What it tells us is that over a second of time, the car moves 2 meters. Over half of a second, the car moves 1 meter, still at a speed of 2 meters per second. Over 1/10 of a second, the car moves 2/10 of a meter, still at a speed of 2 meters per second. And so as the interval of time decreases towards 0, we approach a point where we can say that the speed of the car at time t equals to 0 is 2 meters per second, which isn't very accurate because no time elapses at that one point. But this is a working simplification, which we can use when talking about the speed of the car at a specific moment of time. I'll make 3 important points for a more complete understanding of differentials. First of all, while dy and dx are not numbers, they are important because of their relationship dy over dx, which describes the stretch, or in other words, the slope of a curve at a specific point. So dy and dx go hand in hand with each other. The second observation is that we watched the point approach the origin, so the coordinates of the point were the x and the y distance of that point from the origin. However, we can also find the instantaneous slope of the curve at any other point along that curve. Finally, when we write dy dx, we are not stretching the y-axis, but rather we are expressing by how much the function y of x stretches the x-axis at a particular value of x. This is the slope of the curve of this function at that x value. We can also write it like this. Suppose we are looking at a nonlinear function, y equals to x squared, for example. How do we find the instantaneous slope or stretch of the function at the point where x equals to 1? If we zoom into a point along this curve, will we approach this infinitesimal shape with a curved, so to say, hypotenuse? It turns out that the answer is no, because we can always identify a point along the curve of this, so to say, hypotenuse, such that if we rotate this shape by, for instance, 20 degrees, this point is the lowest point along this hypotenuse curve. We can then subdivide the dx differential infinitesimal into two segments, the one to the left and the one to the right of this point. But this defies the definition of an infinitesimal as something that cannot be further subdivided, which means that this dx value is not the minimal possible dx value. So as we keep zooming in, we must be approaching a triangle, because only the triangle cannot be further subdivided. Any point along the hypotenuse of the triangle can only be identified uniquely by the ratio of the length of the segment to the left of it to the segment to the right of it. But since the length of the hypotenuse is the square root of the sum of the squares of the differentials dx and dy, it is a differential itself, and therefore it is not really a length, so it cannot be further subdivided. But wait, if an infinitesimal cannot be further subdivided, how can one differential be a multiple of another? This is unusual to grasp, but differentials are not real values, so we should not think of them as of lengths, but rather their utility is to, through their relationship, convey the notion of pure stretch, or as we visualize it, the slope of the curve of the function at a specific point. So dy is not twice as long as dx, because length is irrelevant here. This slope of the curve at a concrete value of x is what we call the derivative of the function at that x value. We can plot out the derivative of a function at each point. This will create a new function, which is known as the derivative of the original function. So if the blue function represents the position of a car over time, the red function, the derivative, represents the velocity of the car over time. You might have heard that the integral is the reverse of the derivative, and you could then suppose that since the derivative maps position to velocity, the integral would map velocity to position. And you would be right. The integral, labeled here with blue capital F, would represent the position of the car over time if the red function f of x represents the velocity over time. But we are very obviously making the assumption that at time 0, the position of the car is 0. Does this have to be true? It turns out that it does not. No matter how much we shift the blue curve up or down, the derivative, or the red curve, will be the same, because the slope does not change at any point along the blue curve. Which means that when we take the integral of the red curve, we have to take into account that any arbitrary constant might be added to the value of the integral, or the blue curve, allowing the initial position of the car to be a value other than 0. I will explain to you why this can be done in the very first video on derivatives. What we can do with confidence, however, is use the integral to find the distance that the car has traveled between any 2 points in time. Let's say time 0 and time 2. Let's use our understanding of derivatives to explain integrals. At any point along the curve of a function, it is fair to say that the differential dy is equal to the differential dx stretched by the slope of the function at that point. Going back to our car example, this is equivalent to saying that the slope is a measure of sensitivity of the distance y to tiny changes in time around that moment. Note that we are looking at the slope of the blue curve, but we only know the red curve, the derivative of the blue curve. This means that for any value of x, red f of x equals to the slope of the blue curve at that x value. This means that in our expression for the differential dy, we can replace slope with f of x. Let's take a look at what this means at a specific x value. The dx is simply an infinitesimal representation of the point along the x-axis, while f of x is the value of the derivative at that x. So their product, dy, is the area of a rectangle of differential width dx and real height f of x. The units of this area would be velocity from f of x times time from dx. Velocity times time equals to distance. So as we could expect, dy represents the infinitesimal distance traveled over infinitesimal time dx at velocity f of x. As you can see, when we integrate, or in other words reverse engineer the derivative to find the original function, we break up a ratio representation of slope into a linear equation representation. This way we can only get an infinitesimal value at each point. So for our car model, over an infinitesimal amount of time, the car can only move an infinitesimal distance. To find the real distance traveled, we have to add up all of the infinitesimal distances in that stretch of time, effectively finding the area under the curve of the derivative function between the 2 points. This is a great illustration of the stretch that I was talking about. The derivative indicates by how much the original function stretches each point. The area under the curve of the derivative over an interval is therefore equal to the length of that interval multiplied by the average stretching in that interval. Calculus 1 teaches how to compute derivatives and integrals, with more advanced methods of integration discussed in Calculus 2. In Calculus 3, you will apply methods from Calculus 1 to functions of multiple variables, multivariable calculus. So far, we have discussed the intuition behind derivatives and integrals, but we still do not know how to compute them. In order to do this, we will first have to discuss limits, which will bridge our conceptual understanding with actual computation. We will begin discussing limits in the next video, although we have already mentioned them anonymously in this video.